Hey class, we've been talking about species interacting, and the process that results from that is competition, or at least one process that results from species interacting, and that's when two species have very similar resource requirements, or another way of saying that is they share the same niche. And we've introduced this term fundamental niche versus realized niche, and we're going to build on that today by looking at the outcome of competition between two species. And if I give you some information about those species, about their resource requirements, about their competitive abilities, you should be able to predict mathematically whether or not they're going to be able to both survive or whether or not one species is going to outcompete the other. And in fact, you should be able to tell me which species is going to outcompete the other species. And you can say to yourself, well, I don't know how I'm going to do that, Mike. That sounds like a tall order. But that's exactly what we're going to talk about. And it's going to be based on the model that we reviewed briefly in the last video, that model of competition between two species, where we took the logistic population growth model and we expanded it to allow for not just competition within species, but competition between species. And then we looked at two equations at the same time. And just to refresh your memory on what the heck I'm talking about here is, let's go back to the very first population growth model we worked with. And that's a simple model where R times N, where R is the intrinsic rate of increase and N is the number of individuals in a population. You multiply those together and you get the change in population size over a period of time. And in this equation here, I'm actually got R1 and N1 to signify this is the R for species 1 and the number of individuals N for species 1. And the reason is because now we're going to start to talk about two species. And so we're going to need an equation where all the subscripts are 1s and an equation where all the subscripts are 2s. So we could talk about the R for species 2 and the N for species 2. Now, if we had a model of population growth like this for one or two species, both species would be growing exponentially. Because what we're saying in this model is that there's no relationship between the population size and the rate that a population grows. And we know that that exponential model of population growth is sort of okay for very short-term conditions where resources are plentiful, but it's not going to work over the long term, where we've found out that resources become scarce, and as we saw before, as individuals compete for the same resources, their birth rates and death rates will change. Birth rates go down and death rates go up, and the population slows down. In that case, we said we want to think about maybe slowing down as a logistic model of population growth. And then I said the easiest way to envision this is to assume as the population gets bigger that the effective R, that is births minus deaths, goes down. And so we added in this term here, and we made the logistic population growth model. And that K minus N divided by K, all the subscripts being 1 because it's species 1. That helps us to scale the rate of population growth. And as the population approaches K, this whole thing gets closer to 0. Now, this is all review, right, which is great, because now what we're going to do is we're going to look at the last thing we did, which was to build in now competition between species. And what that really effectively does is two things. It doesn't just change the effective carrying capacity of a population, it also changes the rate of growth when there's no individuals or small number of individuals in the population. And that's because this species is now competing with a totally different species that isn't in this equation. Right? It's another species in a separate equation where we have the change in species 2, N2, over time. And so if there are a lot of those species, what it does is it pushes down this rate of growth of species 1. And that's reflected here by the fact that we're adjusting R by the number of individuals of species 2. Right? Now, refer back to the previous video on where we came up with this equation if you're confused at this point. But what I want to do is put you on the same page of thinking about how these three models fit together. What's happening in this new model is we're changing the rate at which a species grows when its population is small because of competition with another species. But then it's also limiting that species to a certain carrying capacity, which is effectively smaller than it would be if it was on its own. Because now there's other individuals of another species in the environment hogging up resources. And so you can't fill up that environment with as many individuals of your own species as you would have been able to without the second species. So this is the effect of competition in that model we introduced. But now we want to use that model to ask whether or not two species can still coexist in that same space, even if they're competing. So in that last video, we talked about the conditions for coexistence, and I want to sort of refresh your memory or test your memory before we go ahead and explore that with empirical data or experimental data. True or false, competing species are more likely to coexist if their growth rates, that is R1 and R2, increase.